So now let's look at complex exponentials in discrete time. The learning objectives for this section are quite similar to the one from continuous time, so I'm not going to repeat them here, but basically we want to be able to understand what's going on with complex exponentials in discrete time. So we have a very similar story in discrete time as continuous time. And that's similar, not exactly the same, but one thing we can start with is a complex exponential signal is of the form c times alpha to the n, where c and alpha are complex numbers. So we could write alpha as e to the beta, so then we have exactly kind of the same form where basically it's e to the beta n. But it's often more convenient to write things as just a function of alpha to the n, because often we end up doing things with the geometric series, so we want to sum up alpha to the n from n equals 0 to infinity, you get 1 over 1 minus alpha. So this is kind of why we stick with this version of it and not explicitly with e to the j something. So focusing on the real case where c and alpha are real, we can have monotonically increasing, monotonically decreasing, or alternating exponentials. So here we have something that's increasing, it's slightly bigger than 1.1 to the n. And then we have something decaying, which is 0.9 to the n. And then we have things which are alternating. So we have minus 1.1 to the n. Well, it's increasing, but it's flipping sign as it goes along, because the minus 1 is flipping sign as n goes along. And then we can do the same thing with this decaying version, right? So the picture is a little bit different than maybe you have in your mind for real valued complex exponentials, real valued real exponentials. So what about the general case? Well, again, we can write out, now this time instead of writing e to the a t and using the Cartesian form for a, here we're just going to write alpha and c, both of them in magnitude phase form. So we just get c times alpha to the n, absolute value of alpha to the n, times e to the j omega naught n plus theta, where theta is the phase of c. And then just Eulerizing this exponential, we're going to get the cosine and the sine terms. And you can see each of these cosine and sine terms are modulated by a decaying exponential, so we're going to get very similar looking phenomena as we do in the continuous time version. So for example, in this plot here, we again have these this is 1.1 to the n, this is 1.1 to the n, and this is minus 1.1 to the n, and we're going to get this cosine which bounces in between those two. If you want to have it decaying, then you can look at one where there's a decaying exponential and this cosine is bouncing in between the two. So what about periodicity? We had the case for the continuous time where we just took 2 pi over omega naught and we had the period t naught. But for the discrete time case, it's a little bit more complicated. So if we can add or subtract any integer multiple of 2 pi to omega naught, then we're going to get the same thing. So if we have e to the j omega naught plus 2 pi k times n, so now we have k times 2 j times 2 pi k, that's just 1 to the k, and we just end up getting e to the j omega naught n. So this means we can think of omega naught as sort of taking values in an interval of length 2 pi, so we don't have to worry about omega naught, like arbitrary omega naught, but basically only, if you like, omega naught modulo 2 pi. And so we can think of it as either being between 0 and 2 pi, or minus pi and pi. And so for xn now to be periodic, we need that there's an integer n such that I multiply omega naught by n, so that as I go omega naught n times, I look at time capital N, that I get back, that I essentially get back to where I started, or rather it gets to a multiple of 2 pi. So we need that omega naught n, capital N, is equal to 2 pi m, which means that omega naught over 2 pi, this number over 2 pi has to be a rational number. It has to be some m over capital N. So this is a rational number. And so you can imagine there's lots of omega naughts for which this is not true. Like you could make omega naught equal to square root of 2, and then you would be stuck. There's no rational number which is equal to the square root of 2 over 2 pi. So not all dt complex exponentials are periodic. So we have to have this 2 pi over omega naught be a rational number. But if we do have that, then the fundamental period is the smallest capital N such that there's an integer m where we have this n is equal to m times 2 pi over omega naught. And this is, again, let's just re-emphasize, this is very different from continuous time. So there's an example in the book by Oppenheim and Wilsky, which I'm excerpting here. So we have a case where xn is cosine 8 pi n over 31 in discrete time, or 8 pi t over 31 in continuous time. Then the continuous one is periodic, and the discrete one is also periodic, but with a much bigger period, because you can't have the period be some kind of fraction here. It has to be an integer, so we're going to have 31 here. So we had this notion of harmonically related exponentials in discrete time. These were complex exponentials whose frequencies were integer multiples of our base frequency omega naught. So we can do the same thing in discrete time. So we let our omega naught be, say, 2 pi over capital N. That's a complex exponential with period capital N. And then what you can do is you take integer multiples of that. And then you'll get, we can call it phi 1 of n is e to the j 2 pi over n capital N times n. And then we can have times 2n, times 3n, times 4n, times 5n, little n, that is. And we get these kind of phi k of n, which is e to the jk times 2 pi over capital N times n. And these are called the harmonically related exponentials. And for this phi 1, these are called the capital nth roots of unity. That means they're all nth roots of 1. So if I raise these to the capital N, I'm going to get 2 pi times n, which is an integer, so it's just going to be e to the j, something like 2 pi n, which is equal to 1. So this is kind of like so if you like, this thing is equal to the capital nth root of 1, right? And for every value of little n. So when we look at these harmonically related exponentials with integer multiples of omega naught, we have we can sort of see that there's actually only capital N uniquely harmonically related exponentials. So there's little n can range from 0 to capital N minus 1, or 1 to capital N, depending on how you want to feel about it. So let's do an example, because I think that sort of makes things a little bit clearer. So let's take capital N equals 6. So omega naught is 2 pi over 6, or pi over 3. So this is a signal which has period 6. So we can write it from 0, n equals 0 to 5. That's one whole cycle of the signal. And so we can write out what these are. So the nth roots of unity, why are we calling it the nth roots of unity? Because they're basically evenly spaced around the unit circle in the complex plane. We're going to have 2 pi over 3, 4 pi over 3, 1, 2 pi, 4 pi over 3, and 5 pi over 3. So that's this one, this first one. And then in phi 2, we're going to do jumps by 2. So it's going to k is equal to 2. So we're going to do 2 pi over 3, then 4 pi over 3, then 6 pi over 3, which is 2 pi, and then 8 pi over 3, and 10 pi over 3. And for phi 3, we're going to multiply by multiples of 3. So it's actually just going to bounce between plus 1 and minus 1, and so on and so forth. So here we're making some simplifications in the table, but basically we're just jumping around. We're jumping in steps around the unit circle, right? And we're actually only taking 5 steps, or the 6 steps really, around the unit circle to get back to the origin. That's what's going on in this table here. So, what are the differences between discrete time and continuous time? Well, for complex exponentials, well, in continuous time you can have any frequency, and in discrete time you can have only frequencies between 0 and 2 pi, or minus pi and pi. Complex exponentials in continuous time are always periodic, whereas in discrete time you have to have this special integer condition, omega naught over 2 pi has to be a rational number, and so capital N, the period, has to be an integer. We have the fundamental frequency is omega naught in this in continuous time, but it's actually omega naught over m in the continuous time, discrete time setting, and the fundamental period is looks very similar, but we're going to have this integer condition in discrete time, so that this capital N is an integer. So these are the main differences, and we'll explore these differences a little bit more, and when we talk about how these get used, especially when we talk about Fourier transforms. But I want to introduce the ideas now so that you kind of have it in the back of your mind as we go along.